Welcome to part 3 of our lecture video series for Friday, April 21st, where we practice calculating the change in internal energy of a system based on information given about how much heat is either absorbed or released from the system and how much work is done either on or by the system. So let's remind ourselves about the total internal energy of a system, delta U. So the change, delta U, in the total internal energy of some chemical system has been described as the sum of heat and work. Remember, heat is something that we can now quantify that is based on the material, how much of it there is, and the temperature change associated with that material. And work is the amount of pressure volume work as a result of compression or expansion that's happening in our system. So let's just kind of remind ourselves. Q. Remember, Q is equal to M times C sub S times delta T, or if we're looking at the intensive version of Q, C delta T, though this is the one that we typically use the most. And then work is negative P external delta V, or you can do this as P internal delta V, where P external and P internal are assumed to be equal and opposite. So I am going to rewrite delta U so that it is still heat plus work, but it is now going to be heat as M times our specific heat, so MC delta T, plus work, so plus a negative is going to become a minus, minus PXT delta V. All right. So for example, let's look at maybe a simple example first, and then we can add some complexity to this a little bit later. So this is our total internal energy of a chemical system that's typically seen in Chem 210. So let's look at kind of like a more basic example, and then we can maybe add some detail in another video depending on, how we're feeling. So let's see here. How about we talk about a gas sample in a piston is supplied with 524 kilojoules of heat while the piston compresses the gas from a initial volume of 10.0 liters to a final volume of 5.0 liters at a constant pressure of, let's do 4.60 atmospheres. What is the change in internal energy of the system? So let's see if we can't figure out what's going on here. A little sketch always helps. So we've got a piston, which is again just a cylinder that can then be depressed. So we've got some gas inside this piston, and that gas occupies some initial volume of 10.0 liters. And then we have a compression that is happening here where our piston, which is kind of like our little depressor here, is now going to depress so that our volume is cut in half. So V2 or V final is equal to 5.0 liters. And the external pressure that is responsible for this compression is 4.60 atmospheres. And okay, this information all seems to be related to changing in pressure and volume. So this is going to be my PV work information for my delta U calculation. So then what about my heat information? So I'm told in the problem that my gas sample is supplied with 524 kilojoules of heat. So we have 524 kilojoules of heat supplied to the gas. All right. Let's see if we can't put some of this information together. So I know that change in total internal energy is heat plus work. I was not given any information about the gas's mass or its specific heat capacity or even the temperature change that happens as a result of this compression. All I was told was that 524 kilojoules of heat was supplied to my gas. So let's think about what this might translate into mathematically. So I've got 5.24 kilojoules, so that's, 524 kilojoules of heat. And the key in figuring out what the sign of my heat is going to be here is in this word supplied to the gas. So this means that thermal energy is being pumped into my system, supplied to my gas. So what does that mean in terms of my sign? So inward toward the system means we're going to have a positive sign. So we have positive 524 kilojoules of heat, or expressed in joules, that is going to be positive 5.24 times 10 to the 3 joules. Okay, so we've got Q. What about our pressure volume information? So I think it looks like we need to actually calculate the amount of work that's going on in this compression. So let's look at how we can calculate work. So recall, work is the product of the external pressure that is being supplied to the system, or exerted on the system, I should say. That's why it's now negative P external, times the change in volume. So for us, let's see here, we knew that the external pressure was our 4.60 atmospheres of pressure. So that's 4.6 times the amount of just regular atmospheric pressure. And then my change in volume, I started at 10, wound up at 5. So final minus initial, this gives me negative 5.0 liters was my change. So then if I am going to figure out my amount of pressure, volume, work, I need to take this product, which will ultimately become positive. So I've got 4.6 times 5, and then to 2 sig figs, which is all I have anyway, it's a whole number. That is 23, and this is liter atmospheres. So I've got my work, however, my unit needs to be in joules. So I'm going to just bring back a conversion factor where 1 joule is equivalent to 101.325 liter atmospheres. So if I've got 23 liter atmospheres, and I know that 1 joule is equal to 101.325 liter atmospheres, then I would do a division. So taking that 23 liter atmospheres and dividing by 101.325 gives me, let me just check that conversion real quick. I have this backwards. I knew that was giving me a tiny work. Let's see here. 1 liter atmosphere is 101.325 joules. So then 101.325 times our 23 liter atmospheres gives me 2,330.475. And let's see here. Number of sig figs would be 2. So technically, I'm just going to write this whole number first, and then we'll get our sum. So this is our work. And notice the work sign is positive work. And let's make sure that this makes sense. This implies that we have work done on the system. So a force is being supplied, or a force is being applied that is pushing on our system, causing it to have a change or displacement, or here a change in volume inward. So we're looking at compression. So this does make sense that we would have a positive sign on work. So let's see what the total internal energy change of our system is. So we were given 524 kilojoules, or 5.24 times 10 to the third joules of heat, plus my work, which is 2.33, and technically it's 2.3 to 2 sig figs, times 10 to the 3 joules of work. So this is my heat Q. This is my work W. All right, so let's see here. What if we were to like actually add these numbers? So $5,240 joules of heat plus 2,330.475. I am dropping a comma in my calculator. 5,240 joules of heat plus 2,330.475. Again, we're using our unrounded values to get our actual quantity. Okay, now putting this back into joules. So this gives me 7.57 times 10 to the 3 joules, or with rounding, 7.6 times 10 to the 3 joules. Or if you want to determine this in kilojoules, this becomes 7.57 kilojoules, or to the correct number of sig figs, 7.6 kilojoules, meaning that the change in total internal energy of our system is 7.6 kilojoules, and notice this is positive. So let's kind of make sure that we're doing everything right here. So if we have a positive change in total internal energy, this means that we have to be absorbing heat and having work done on us. So this means that energy is transferred to system and work done on system. Two ways of saying the same thing. We had thermal energy that was indeed transferred to the system as heat, right? And then we also had work that was done on the system because we had compression. So we have this positive sign in our change in total internal energy of our system, which tracks with what's going on here in terms of how heat and work are being transferred. Okay, I think I'm going to save something like this for a little bit later because there's a little bit more to the story, but just know that you have the tools to be able to use this equation if you know something about heat or work, or if you know something about total internal energy. And let's see here. I think for today, I think we're good. I don't want to start talking about enthalpy quite yet. So let's save enthalpy for Monday. So here today's 21st. Let's be the 24th. And we'll also begin with a warm-up that perhaps utilizes this equation coming up on Monday. And then, like I said, we'll be talking about enthalpy. So we have wrapped up our conversation about how to calculate heat and how to calculate pressure, volume, work, and use that to make calculations about a total internal energy change of a system. And moving forward, we're now going to add in enthalpies to the equation so that we can talk about heat transfer and calorimetry coming up next week. So I will see you all on Tuesday for our review and our wrap up of the Copper Cycle Lab. And with that, have a lovely weekend. See you guys.